Last month, Hammerspace unveiled a new storage architecture called hyperscale NAS that addresses the needs of AI and GPU computing. This episode of the On-Premise IT podcast, sponsored by Hammerspace, is focused on the extreme requirements of high-performance, multi-node computing. Eric Bastier of Hammerspace joins Chris Grundeman, Frederick Van Haren, and I to consider the characteristics that define this new storage architecture. Welcome to the On-Premise IT podcast, the only show that dares to be both on topic or on premise, and sometimes on location or on premises. Each time we meet, we bring together a group of IT experts to discuss a single idea. Today's premise, brought to you by Hammerspace, is the question of storage architectures. AI and GPU computing demands something pretty new. The conventional scale-out and scale-up NAS just won't cut it. Before getting into that premise, let's quickly meet who's on the panel today.
Hi, my name's Eric Bastier. I'm Senior Director of Solution Marketing at Hammerspace, and I've got over 20 years of experience in data storage and data management in a number of different companies.
I'm Chris Grundeman. I am an independent IT analyst and consultant, also with 20 years of experience, but not as directly related as Eric's.
I am Frederick Van Haren, the founder of HiFence, which is a consulting and services company active in HPC and AI.
And I am Stephen Foskett, organizer of the Tech Field Day events and host of this here podcast. So Eric, Frederick and I were at AI Field Day last month, and we got a chance to hear about something pretty new from Hammerspace. But of course, we also heard a lot of other things at AI Field Day from a lot of other companies. Still, I think that it's safe to say that throughout all of it, we hear, number one, that there are different phases of AI. And by the way, if you're interested in that, we have a podcast called Utilizing AI that we're publishing every week as well, where we can talk about that in terms of AI infrastructure. But ultimately, AI training is a lot more like HPC than it is like any other application, because you have a ton of clients all accessing the same data. And frankly, traditional storage architectures just weren't made for that. So without stealing all of your pitch, tell me a little bit more about your position on AI and GPU computing and HPC and the storage needed to support training.
Yeah, well, at the AI Field Day or the day before, we made a pretty exciting announcement for us, and we unveiled a new storage architecture that we call hyperscale NAS. And this architecture was built for AI and GPU computing. And it largely came out of our work with one of the world's largest hyperscalers for their large language model training environment. So it is a new storage architecture. And what we're now talking about is why, as more and more enterprises get into AI, drive forward their AI initiatives, why this is the best storage architecture for large language model training, generative AI training, and other forms of deep learning.
So, first thing, I just want to take a moment to say that I love the name Hammerspace. And I don't know if people understand where that comes from, but just the idea of being able to kind of pull things out of thin air from cartoons and stuff. Anyway, look it up. Hammerspace means stuff other than just this company, and it's really neat. That said, the other thing I like about Hammerspace as a company is, it seems anyway from the outside, a real dedication to building things in a standards-based way, right? And I think this hyperscale NAS appears, at least at first blush, to be a representation of that, or another example of that. You're using kind of standard TCP/IP stacks. There's no proprietary client software needed. This really just works as a NAS, but in a really new way to support these kind of crazy GPU workloads we're talking about in AI.
Yeah, that's right. And it's interesting you mentioned the name Hammerspace. I mean, a Hammerspace is, depending on the definition, it's an infinitely scalable, instantly accessible area where you can get, whatever you need from it. And we named the company that because that is the way we think about our software platform, as a way to give any user, any application, instant access to whatever data they need, whatever files they need. And you're right. In fact, Hammerspace as a company was incorporated in 2018, and we've been growing very quickly. But one other interesting thing that happened in 2018. And one of the things that has been in the underpinnings of Hammerspace's architecture since day one is this use of two capabilities that are built into the NFS 4.2 client, parallel NFS, and then flex files. And that flex files, technically it's a layout type. It's an optional capability of NFS 4.2. It was engineered by Hammerspace and made part of the NFS 4.2 spec back in 2018. And basically those capabilities define a standards-based parallel file system architecture using NFS. And now the Hammerspace software, our file system, is the first to take advantage of those capabilities. And that's why this architecture is so new, so unique.
So a lot of organizations are already doing AI and have a variety of AI storage solutions. So how does that work with Hammerspace? Do people have to throw away all of their old storage devices? Are you targeting greenfield or is it more brownfield? How does that work?
Either one works with Hammerspace, and I think we see customers and we see use cases where both may apply. Our experience and my perspective is that every enterprise is in a little bit of a different spot in terms of their AI journey. Some may have just procured and they're deploying a lot of GPUs, and now they're going to be building out the underlying infrastructure. Others have been doing different forms of AI and machine learning for many years. Hammerspace software is unique in that it can run on commercial off-the-shelf storage servers. So for example, one of our customers just uses OCP storage servers with NVMe inside, and they just layer Hammerspace on top. But we can also run Hammerspace or install Hammerspace on top of an existing storage infrastructure. That could be NAS storage, it could be object storage or block. And even in those cases, you could think about Hammerspace as sitting kind of between the GPU clients and the underlying storage. And we've even seen in some cases, we can speed up that underlying storage just by layering on Hammerspace kind of between those GPUs and the underlying storage.
Yeah, we see regularly customers struggling with metadata, where metadata is really being the bottleneck as opposed to the actual data. And how does Hammerspace help with optimizing the metadata?
Well, let's start with just the basics on Hammerspace's our architecture. And one of the things that's unique is we split the metadata and the data into two different paths in a sense. So in a way, you could think of a control plane and a data plane. Hammerspace being the control plane, and at the core of that is Hammerspace metadata services nodes. Now, in this architecture that we call hyperscale NAS, it really brings together the best of a parallel file system architecture with standards-based NFS or NAS. And the way that works is the client, so let's think about like a GPU server as a client, that can have just Linux running on it. And we leverage that NFS 4.2 client. We split the metadata and the data path. So metadata goes to the Hammerspace metadata services node, which we call an Anvil. Then there is a direct data path between that client, let's say the GPU server, and the underlying storage. And that could be, again, off-the-shelf NVMe storage or whatever the customer has. By doing that, and again, we separate that control plane from the data plane, we're able to do a couple of things. One, we reduce the number of network transmissions and retransmissions that have to happen between the client and the server. So we establish a direct path. So we're able to get much lower latencies, much faster throughput. Two, we offload a lot of those metadata operations to that separate path so we can streamline that as well. And that's kind of the core hyperscale NAS architecture, where you've got this Linux client. It can be any modern Linux OS. It has that direct data path right to the underlying storage server. And then we take metadata out of band. And again, it's about separating that control plane from the data plane.
Right. And so when we talk about training, I mean, one component of obviously is processing data on your GPUs. The other component is researchers sharing their findings across the board. How does Hammerspace help with collaboration with researchers and improve the process?
One other unique aspect of Hammerspace's architecture, we can provide that direct data path between the GPU clients and the underlying storage servers. But of course, we also support other standard protocols, NFS, SMB, researchers that are connecting over, for example, a Windows operating system using SMB. They can all connect and see the same underlying file system. They can all access the same data simultaneously. And uniquely with Hammerspace, we can extend that global parallel file system to not just multiple protocols, but actually multiple data centers, even if those are different clouds. So in that example, we create a global parallel file system with a single global namespace so that even users that are remote or not co-located with the data are all presented the same files that they're authorized to see.
Yeah, I think that's an important aspect of the solution too, is that it basically creates sort of a giant, uh, a view of a giant NAS that stretches multiple locations or multiple backend devices and so on, so everybody can see the same data. It always strikes me as a storage nerd that normal people assume that's how it works. I think normal people assume that if we have a whole bunch of different locations, a whole bunch of different file systems, a whole bunch of different whatever, everyone everywhere can access them because that's how it should work. But it is definitely not how it works in most conventional storage systems. And similarly, I think a lot of people assume that their enterprise storage solutions are incredibly scalable and high performance, and they are to a certain extent, but they're not built for the kind of access that AI and HPC and other workloads put on them. So I think hyperscale NAS represents a big transition for Hammerspace because, traditionally I think that it was more access your data anywhere as the pitch. And now I think that this whole concept of performance and supporting HPC and ML applications, talk to us a little bit more about the unique demands that required something so radically different.
Well, I think one perspective that we've heard and that we're talking about is I think AI is forcing a reckoning in the industry that's probably long overdue to change how data is used and how it is preserved. And it's for the reasons you just mentioned, Stephen. Architecturally for us, one of the I guess problems we've seen in the industry is many of the infrastructures out there have what we would call a storage centric architecture or a storage centric design, where things like the file system are trapped at the storage layer and you don't get that global view. Fundamentally with Hammerspace, what we've done, and this was back since the company was founded, is elevate that file system out of the storage layer so that you can get that global view of all of your data across sites and across different storage silos. Now, in terms of some of the unique demands for AI, and I'm going to put a little bit of Hammerspace's perspective on this, I want to talk about three things that we see as AI infrastructure challenges and kind of how we address those, and then it'd be great to hear from the team here. First is just to train effective models, you need massive data sets, right? You want to train them on billions of parameters and more. Often that data, unstructured data, is trapped in different silos. It could be different cloud storage buckets. It could be different NAS systems or whatever. Hammerspace can help solve that by basically sourcing data from any existing file or object storage system and then bringing that into our namespace. We do that through a process that we call assimilation. We could talk more about that. So one is just assembling the data set. Two, you need that performance especially for training, later maybe for inference, but especially for the training step. That's where you really need a system that has that extreme HPC-like performance to feed all the GPUs to keep them utilized. And then lastly, most enterprises either have users that are not co-located with the data, or it may be that the GPU resources themselves are not co-located with the data, and you need to have the ability to place data where it needs to go. That may also, take the form of, once you've created a model, you want to do something with it. You need to maybe archive it or protect it. So, and we do that through global data orchestration. And so we view like assembling the data, helping with that through assimilation, training the data with this hyperscale NAS architecture to feed GPUs, keep them utilized, and then global data orchestration to place data in a way that is transparent to the users. And I think that's kind of our take on how we can help simplify AI and machine learning data pipelines.
Yeah, nowadays when we talk about AI storage, we typically talk about performance and low latency. In most of my conversations, I add the concept of data management. So an example of that is an AI. You have billions and billions of files. It's great that you can process that data really fast, but you need to find your data first, right? And so as far as data management is concerned, is where is my data? How is it structured? Because a lot of time can be wasted finding files, right? I mean, you could ask for something and it be gone for hours, right, before it returns, which also will hurt you eventually. So can you talk a little bit about the data management features of the Hammerspace file system?
Yeah, for sure. It's another key benefit of separating out the metadata layer from the data layer. And so at the core of our metadata services node is a database of metadata that can be queried. And then we can also use that metadata to take different actions on the data. And to take different actions on the data.
Circling back to the kind of the performance aspect of this, I think, one, the implications of having all the data accessible is, I think, pretty obvious, right? That being able to point the training, the inference, have different workloads working at different times and be able to access all of that data, have it be managed. This all makes a lot of sense to me. But the performance is also important, right? And you're in this kind of mixed IO environment a lot of times with AI type stuff. And maybe more specifically, I'm wondering if there are specific things that Hammerspace is doing to increase performance, because again, we're talking about, as I started, early on in this conversation, with this kind of really standards based, right? So you're using existing Ethernet, existing InfiniBand. There's no, needed, extra client software. You're using potentially the existing storage infrastructure itself. So is there much room for Hammerspace to actually increase performance, or is it really just kind of collecting and managing the data in a more sane and reasonable fashion?
Where we increase performance, I would say, is specifically relative to scale out NAS architectures, which are kind of the predominant one used. And when the way we talk about a hyperscale NAS architecture, it is about bringing together kind of an HPC parallel file system architecture with enterprise NAS, reliability, availability, and serviceability. So, I think the key thing architecturally that drives that extreme performance is that direct data path between a Linux client and a server, right? And if we compare sort of like the networking or the data retransmissions that have to occur in a scale-out NAS architecture, you have the Linux client, you got a switch, you got a NAS controller, another switch, and then the storage. And so there's a number of network hops that need to happen. What we do is we take out about half those network hops. So we're going directly from a client to the underlying storage, right, with metadata out of band. Now, and that sounds a lot, and it's correct that is very much like an HPC parallel file system architecture, like a Lustre or a GPFS, or maybe like a less mature one might be like Weka. But again, for the people listening too, the key difference with that Hammerspace architecture and those others, they rely on a proprietary client or a proprietary file system client or agent that sits on that GPU server to give them that intelligence. What we've done is we've built that into NFS. The architecture is very similar. It's just that we use the NFS 4.2 client that's in every modern Linux kernel. And it's why our CTO Trond Mikkelboost is the Linux kernel maintainer. It's why that internal IP that we have and the internal expertise we have is so important. So, I mean, there's always going to be things we're going to continue to do to tune performance, to do that. I'll segue quickly and just say the underpinnings of this architecture have been in Hammerspace since day one. Why are we announcing this now? Why are we bringing it to market now? And it's because of everything we've learned where we've now proven this architecture at hyperscale. So one of the world's largest web properties is using this in their LLM training environment. And just to give everybody a sense of scale there, their GPU cluster now is over 30,000 GPUs across about 4,000 server nodes. There is a 1,000 node Hammerspace storage cluster that is feeding those GPUs at aggregate throughput of around, or aggregate performance of around like 100 terabits per second. I mean, it's 80 to 90% of kind of line rate. And it is, and again, what they liked about this so much, the reason they chose Hammerspace was everything standard based. They used Linux on their GPU clients. They used Linux on their storage servers. All they needed to run on the underlying storage servers was Linux. So it is very much like a parallel file system architecture, just everything standards based.
Yeah, I think that's important. Also, it's no trick that you managed to make sure that this is in the standard, because as you mentioned, Tron maintains PNFS in Linux and is the manager of this. A lot of this, I think that the hyperscale NAS, am I wrong in saying that it requires PNFS 4.2, right?
Yeah, so a little bit of background there. Technically, it would be the NFS v4.2 client that's sitting on the the GPU server, and then there are, I'm oversimplifying this or streamlining it, but there are two optional capabilities in the NFS v4.2 client that we take advantage of. One is parallel NFS, and that was introduced, I want to say, in 2010. And then there is what we call a flexible files layout type, or flex files, that was introduced to the spec in 2018, and that was engineered by Hammerspace. And between those two things, what that does is it defines a standards-based parallel file system architecture using NFS. Our parallel file system, Hammerspace, is the first one to take advantage of those capabilities.
In this standards work and kind of have you pushed this forward, I noticed anyway that you have, I don't know how recent it was, but have become gone through the validation process from NVIDIA for the GPU direct storage. I wonder if there was anything, is this something that was easy and you just went and did it validated, or were there other things that had to be tweaked to make that work? I guess I'm asking less about Hammerspace and more about the value of this GPU direct family of technologies.
It was pretty easy for us to do. It just worked because it's just NFS. What was great about it, and what it does illustrate, is in the test setup for that, we used NFS over RDMA, and it was over, I think, a 40 gig Rocky network. And it also illustrates a really interesting benefit of a hyperscale NAS architecture, which is we can use TCP/IP, and we can use RDMA. We can use different data transports, and we're flexible that way. We've also shown, we can either use Ethernet or InfiniBand. Doesn't really matter to us. Our large hyperscale customer is just using Ethernet, and they're getting excellent performance like we talked about. But for those that have an InfiniBand infrastructure or want to use different networking technologies, you get that choice. And GPU Direct, it's a very important technology. NVIDIA is one of our technology partners and an important go-to-market partner for us as well.
And of course, they're also the GPU provider for most of the biggest AI training clusters out there. So it's important that you're working with them. What is it as well that makes this machine learning different from other HPC applications? I mean, certainly there have been massively scalable applications before, and they've gotten along pretty well with things you mentioned, Lustre and GPFS and so on. And Deos. I mean, you got to mention those too. I mean, what is it that about ML training that needs something different?
Maybe more than that. One thing that I would point to is these HPC file systems have never been widely deployed in the enterprise. And they're widely used in HPC, but I think a notion that you guys have talked about and that the industry has talked about is that the rise in enterprise AI is going to be like HPC workloads coming to the enterprise for the first time. And we think the fact that we think about the market in we think about a couple different storage categories for the enterprise, right? One is scale out NAS, one would be these HPC file systems. The fact that the HPC file systems have never been widely deployed in the enterprise, I think speaks to a gap there. They don't have the right feature set. They're too difficult to maintain. In HPC environments, they can tolerate that. They can put engineers on it, no problem, but not in the enterprise. On the flip side, the fact that those HPC file systems still exist so predominantly in HPC environments is an admission that scale-out NAS architectures don't meet their performance, right? And so I think a way to think about AI is HPC is going to be coming to every major enterprise, and they're going to need a different architecture, a new NAS architecture that gives them the performance of these HPC file systems with the right feature set and standards-based simplicity of NFS.
Well, I think, Eric, you've made a case that there is a need for a new kind of storage in these extreme large environments like the ML training and the hyperscaler that you mentioned. And I think that you've made the case, too, that it makes sense to use a standards-based NFS client for it. Chris and Frederick, what do you think of this as we're nearing the end of this episode?
Yeah, I think you stole the words out of my mouth there. The standards-based piece is what really makes this attractive to me, as Eric mentioned, right? Making this really much more approachable and I guess easier to deploy in the enterprise as we do more and more AI in more and more places. We get out of those kind of conventional HPC operations and into more AI is just day to day, but it really does have all these huge requirements. Having this standards-based approach where you're, one, using the standard, but also driving the standard forward for AI uses, I think is fantastic. And I do want to be able to pull an anvil out of the air anytime I want.
Yeah, I definitely think that AI is driven by GPUs. The GPUs are getting faster and faster, which also means you need more access to data faster with lower latency. So there's definitely a need for optimizing storage devices. I also think that collaboration is really important, providing data management features like data gravity, single namespace, and components like that are really key to make training and inference really effective for AI.
Yeah, I agree with both of you, and thank you for those comments. I mean, we're very excited about this announcement, and the feedback we've gotten from the industry has been pretty overwhelming. In fact, people have been very surprised. They kind of say, I didn't expect this. But as they dig into Hammerspace and our architecture and what we bring, I think we're in a very good spot in terms of as AI and these different forms of GPU computing start to be more widely deployed in the enterprise. I think our feature set can really help simplify those data pipelines. And I can say that, several customers we've been working with have been really big proponents of this standards-based approach, as Chris said. You're going to be hearing a little bit more from them in the coming weeks because of their interest in, let's say, just democratizing the ability of AI and to be able to train these models, not only at hyperscale, but really, at any scale. So look for that in the coming weeks, and I'm sure we'll be talking a lot more about it.
Well, thanks so much for joining us today for this episode of the On-Premise IT podcast. Before we go, where can we continue this conversation and continue to dive into these topics, Frederick?
Yeah, you can find me as Frederick V. Heron on LinkedIn and on my website, hyphens.com, which is highfens.com.
Yeah, and I am Chris Grundeman on LinkedIn or chrisgrundeman.com for pointers to all the other things.
And for Hammerspace, please go check out our website, hammerspace.com. We have a number of new pieces of collateral that talk about this hyperscale NAS architecture. Right from our homepage, you can actually link to a great white paper that is an analyst perspective on these different architectures we've talked about and why the hyperscale NAS architecture is needed now. And I think that's a great asset to start with.
And as for me, you'll find me as S. Foskett on most social media networks, including LinkedIn, Mastodon, and X Twitter. And also, of course, you'll find me hosting the Utilizing AI podcast, often with Frederick, every Monday here at Gestalt IT. This episode was brought to you by Hammerspace, as well as Tech Field Day, now part of the Futurum Group. If you enjoyed this discussion, please do subscribe so you don't miss an episode. And you'll find us in your favorite podcast application. But before we go, I have a special thing to mention to all of the listeners. This is episode 432 of the On-Premise IT podcast, which is a big number, much actually bigger than I actually guessed that it was, because we just record this every week. I never really thought about the episode numbers. But this episode is actually the last episode of the On-Premise IT podcast. We are next week launching, what this was originally called, the Tech Field Day podcast. So if you're looking for this in your favorite podcast application, your subscription should move over just fine. But don't be surprised when you see the artwork change, the title change. But what's not going to change is how we do this. Every episode is still going to feature a central premise, and every episode is going to feature a panel of folks from our Tech Field Day community, as well as on the delegate side, as well as the sponsor side. And we really look forward to continuing this under the Tech Field Day name instead of the, somewhat confusing On-Premise IT name. So thank you very much for listening. Thank you for listening for 432 episodes if you're that guy, or for 4 episodes if you're new to the show. And we look forward to seeing you next week.